Hello. Hi everyone. This talk is to kind of motivate fine-tuning as something that you should all be doing. Just by like show of hands, how many people have like seriously in like a production setting deployed a fine-tuned model just to like gauge the like a moderate amount of people? I mean, like the headline like beat GPT-4 is obviously like whatever. It's like a title bait. But I think the more like core concept is that you need to mobilize your first-party data for AI solutions. And to really motivate this problem, I start with this question. What is this article of clothing? This is the Fashion MNIST dataset. It's a successor to the MNIST handwriting digits dataset. But really, it's just like, it's a shoe, it's a t-shirt, and you're pretty good at recognizing it, but I don't actually know what the thing in the middle is. GPT-4o, if you just like paste in an image and go like, hey, what is this image? And you use the language model with multimodal capabilities and just say like, hey, like, what is the result of this? You get 81%. If you use a tree-based model that you can run on the first day of ML 101, you get 90%, which is obviously significantly better. And then finally, you can get to like a ResNet, which like without a lot of tuning, you get to 95%. And models which are state-of-the-art in like 2015 and run on like a tiny fraction of the compute, or run basically on a single CPU for inference, can exceed the capabilities of GPT-4o. And I think this is a motivating point because, you know, if you think in the domain of like RAG, right, and embedding models as like broadly in this like AI ML space, you got about 49% accuracy on like the benchmarks that you can see on Hugging Face for immigration law RAG, which is the AILA statutes RAG benchmark. It gets 95% on web docs. Why? Because Google trained the embedding model once upon a time to go find the accurate web docs, right? So it was the mobilization of data for BERT embedding was to find web docs, and it does great at that. And it was not to find immigration law, and so it works not so well. It's somewhat of like a obvious outcome. And you know, there's a lot of money in this too. Like Voyage AI sold for $220 million to MongoDB for undisclosed amount of revenue because their whole thing was that we make fine-tuned embedding models. And as a company, MongoDB felt like that was really valuable. So there's like a couple of different broad benefits that I won't go into too much detail because I think presuming some level of knowledge, but you know, domain-specific knowledge, task-specific success, and just speed. You can do things better, or you can do things faster and cheaper. And these are kind of like adjustments that you can have depending on the kind of fine-tuning technique and the approach that you take. I'll just reference one example by Databricks. Whatever, the founder of the last company I worked at was one of the authors here, so great job, guys. They took a Llama 8 billion parameter model, and they trained it to generate code diffs to fix code snippets. In this particular case, when compared to GPT-4o, they were, which is 100%, they were about 40% more likely to fix errors, and the latency of the model was over 2x the time that it took to generate tokens from GPT-4o, which is kind of like you can tune between better and faster in that maybe if they use a larger model, they would get even better relative performance, but maybe with a less latency benefit, right? And for this code fix model, if you're in a Databricks environment and they want to be able to fix the code really quickly, you know, speed was actually something they wanted to prioritize, so they picked the smallest reasonable language model who can achieve better results but at speed. And so this is just really to motivate the idea that like it works, like it's been proven to work, and increasingly the state-of-the-art solutions and deploy software are based on fine-tuned models. But ML has always been about winning with data, and without being too negative about the AI labs, there's some kind of motivated reasoning when someone tells you that you can just use Bedrock or you can use OpenAI endpoints and call one model endpoint for everything. And I think ads is a great ecosystem to analogize this by. Imagine if Facebook went out and said, we don't need to build an ML-based ads platform. Google Ads looks pretty good. We're just going to plug Google Ads into Facebook and serve all of our ads through their ML platform. That obviously doesn't work to make Meta a huge company, and that would have made Google a much bigger company. So really, like, the last piece of motivation is like, how many use cases have like moved from ML to LLMs? A few, but if you look at all the companies that are like telling you that you should call their endpoints, they're also all the ones spending billions on CapEx and model training, which kind of motivates the point that you should probably also be building these capabilities, especially if you work at a reasonable scale organization who is going to make a product moat off your fine tuning. And on that point, like ML velocity is fundamentally equivalent to your competitive velocity because ML research is a research discipline. There will be a lot of things you do that will make your model worse, right? Like these are pretty good models which have had a lot of work put into them already. But if you can kind of make the line go up, make your loss go down, your velocity to do that is your competitive velocity. And when you think about it, actually, I think most people are aware of this, but all the models that you've had have been fine-tuned in some way. And like sometimes you're calling it post-training, like there's all this popularity around evals, but the AI labs don't just give you the data set raw, right? Like there's the instruct data set and there's a non-instruct data set. The NVIDIA presentation earlier allows you to train reasoning into the models. And basically, if you think about the ratio, Llama 3.1 was trained on 15 trillion tokens, but it was post-trained on about 25 million synthetically generated tokens. It's kind of saying that the level of effort is how many magnitudes? It's like 3 or 4 orders of magnitude lower to do that. So yes, pre-training a model is like dumb and you shouldn't do that in 2025, but the order of magnitude to actually like go and produce a reasonable change in behavior on the model does not actually require that much data. And since it's already been fine-tuned for behavioral and instruction following, it takes 1 or 2 orders of magnitude, as low as a few hundred labeled examples, to produce novel behavior that is well tailored to your use case. And like maybe like more abstractly, I don't like it when people analogize like matrices to like the brain, but like GPT-4 knows too much, right? Like it knows how to write code and poetry and all these other things, but like you don't need it to be good at any of these things. You just need it to be good at really one thing, and that's where your ability, your domain knowledge, and your first-party data is very influential for this. So just like briefly taxonomize for the sake of structure, right? There's offline and online data that you can feed back into the system. The offline traces and the online success failure tracking are both actually traditional product exercises, traditional engineering exercises, but it does require you to be a little bit creative to think about like what you actually want to collect from the end user. Character AI, for instance, early on would generate 4 low-resolution images and have you select one of them in order to upscale and upsample. But that's a data collection exercise. There's the obvious like stars. In a code correction case, you can take it and see what the code completion, the code diff generated, and then you can compare that against what was actually successfully run next. And that creates a pair of examples which you can then use to further tune your code diff model. There's a range of techniques, and I think speakers have touched on some, if not all of those at this point. I think there's a wide array of techniques at this point, and I think 2 things. One, like Cursor is your friend, right? Like, or like whatever, Windsurf, your choice, Copilot. Use whatever code generation tool, whatever kind of GitHub library that you find, and that goes back to the competitive velocity. It comes from your experiment velocity. There is heterogeneity in the approaches and the techniques that are available to you, and so it's really important that you have the ability to kind of experiment against all of these techniques and kind of combine your various data traces that are collected and thoughtfully assembled with the state-of-the-art techniques to drive the feedback into the system. Finally, like prompt engineering like kind of doesn't scale. Like maybe this is too controversial a statement, but you can like lightly branch your prompts at small scale results, but unless you have a system, right? Like when you think about like traditional ML, like if you think about recommender systems at like Instagram, right? That is a self-learning system that propagates at-scale feedback automatically back into the system. It's not one in which like failure cases are manually logged one by one and you collect them and you like branch your prompts. Prompt engineering is like somewhat helpful for like early things, but at some point like the prompt engineering will kind of be fragile. And then the last part of prompt engineering is like it's extremely tied to the version of model that you have, right? Like it's extremely fragile in the way that unlike when you build a data system to propagate feedback to your model, the prompt engineering path is a manual one that does not actually allow you to take it and apply to Llama 4 and subsequently. Like you start with the off-the-shelf models, you build robust evaluations. I don't want to be so dogmatic about training that I ignore the fact that evaluations is like the P0 for building a self-learning system. But then you build repeatable offline data training loops, and then you build repeatable online data training loops. And the data and the system that you have is your permanent asset, not like the model checkpoint. This is generically true for all other like ML systems as well, right? Like back to like the recommender systems, the model checkpoint is not the value of the meta ML team. The meta ML team's value is in their ability to collect your likes and your shares and your views and train that model every 15 minutes over a cluster of GPUs. And there's always incrementality over the state of the art when you have this first party data set, because no matter what comes out, as long as you're using an open source model, you can always retrain into these. You have the evals, and if someday a model comes out and it's GPT-9 and it really solves your use case completely and you never have any errors again, you can then throw out your data system. But until then, you have an evaluation to understand the relative performance. You have the categories that you have underperformed and overperformed on, and you have that data system to kind of tune it. So then you kind of have the ability to always improve over the state of the art with your data system. This has been covered amply, I think, today. But like fine-tuning is basically just torch training, right? Like people have been training SGLoops models, people have been training torch models. Fine-tuning is not that hard. And like Hugging Face, which is giving a lot of great talks, and also later on, right? They have this trainer class that like wraps it and makes it even easier. And then the various people who have spoken have other wrappers around various subsets of the torch ecosystem. So if you can train a torch model, you can build a better LLM than GPT-4 for your use case. But there is a trap here, which is like LLMs feel different. And like LLMs feel different in kind of the same way that ML has felt different than software. And I work at Runhouse. We're actually like an ML infra company. We're like not solely religiously focused on fine tuning. But LLMs feel different for kind of the same reason that ML has departed from traditional software. Model weights, the models themselves are order of magnitude larger than other deep learning models. The size of data sets and the number of trainable tokens is also very large. There is no local iteration path for training large ML models. There's no iteration path for training LLMs, right? So some of the traditional like requirements of training a model break free from what the pattern of software engineering is, where it's like, hey, like you develop some code, I align my website header differently. I view it locally and I say like, that looks great. And then I push this code and it builds in CI and then goes to production. There is not an ability to do that. And so these two things are the reason why the traditional development SDLC loops feel much harder to do in LLM world. There's also like sometimes not really a target metric. And this is like kind of a product engineering question as well. Like for a lot of organizations when we talk to, their definition of done is having a RAG app, having some kind of AI agent in production, but that's not targeting some kind of improvement metric, right? Like I keep analogizing to these like traditional ML systems, like recommender systems at Meta, because there's billions of dollars being earned on these systems. And like for that product owner at Meta who owns the recommender system, moving that accuracy on some model by like 10 basis points is gonna translate to a promotion in hundreds of millions of dollars for Meta, right? But you have to have a target metric for that improvement gradient to exist. And if your organization's definition of done is having a model in place to like have an AI agent, that's like a little bit of an anti-pattern to like success. And then like, it's actually not costs. Like I kind of want to like make that point as like a objection handling. Like LLMs are not different because cost. You can kind of like fine tune a LoRa model with 13 billion parameters for a few $100s and it gets cheaper all the time. And there's all these service providers who will also sell you compute at below 0% margin to do it with. It's actually like to the point on the first two that the model, the data size, the weights, the requirement for accelerated compute exceeds the bounds of your local development loop. It has created a problem where infrastructure is what gates your experiment velocity. This is where like we start to enter a little bit into the territory of like our opinionation as people who like work in infra all day. But many teams are not equipped with a proper ML platform, right? Like DDP or with Hugging Face Trainer, with Accelerate, with Lightning, all of these things are free insofar as the code required to, the code to write the program is extremely trivial to access. However, how do you experiment with that? Multi-GPU, multi-node fails for notebook-centric, VM-centric, DevBox-centric development iteration loops. But you do need the fast iteration loop still to experiment with all these methods. The problem is that we have no dogma against notebooks, but these are not real AI systems because they're not reproducible, they're not composite, and they lack fault tolerance in production. When you develop through deployment, by contrast, which is what we also see a lot of, where instead of having these like not fault tolerant, not scalable, not reproducible systems, you said, okay, like, well, I'll use Dockerize everything and I'll load my containers up and it will be perfectly reproducible. Unfortunately, you get this developed through deployment process where instead of viewing your website after you realigned it and then pushing it, in order to add a print statement to your program, whether it's an inference application or it's a training loop, you need to actually deploy the whole container through CI. 30 minutes to 3 hours later, it's finally live on your Kubernetes cluster and you can see the results. And like, you need to go the full loop on a fine tuning, right? You have some data iteration, so you write the distributed data program to do the data pre-processing. Then you do the distributed training, which requires a couple loops of iteration. Then when you're done training, you need to deploy this as an inference application as well and do a couple loops of iteration there to make sure that your B version even runs as a B version before your experiment even starts. If all of those iteration loops require you to rebuild a Docker image for every single change, then you don't have a self-service path and it gates your experimentation velocity. And so like this concept that like we didn't coin and like we don't sell anything off of is like experiment escape velocity. The reason why so many exercises don't get off the ground is that the perceived difficulty is so heavy that you actually don't feel like you have the agency to go and launch those experiments, right? I think it holds teams back at large companies and it holds teams back at small companies because the perceived value is there, right? Like I think most people would say, yeah, like at this point we believe that like fine-tuning our models will produce better results. The main problem is that if you can't believe that it's pretty lightweight to launch the incremental experiment, then the expected value is always going to be a little bit negative relative to doing something else. And like the test of whether or not you have like a good ML platform is essentially if you see an interesting repo, like, I don't know, Lightning Thunder, can you like go and just clone that, make some small edits and run it regardless of like what your platform is, right? Like, is that possible? Or are you missing something that allows you to kind of take an arbitrary repo and run it? And so like kind of like moving into this broader conceptual space, I think Snowflake is a great example of doing this in the data space. SQL worked great for single node queries, and then you had Hadoop, right, for multi-node, and you have MapReduces, and you had this fragmented data ecosystem. After Snowflake, whether you were running over 10 rows of data or a billion rows of data, you could do select count star from my table, and Snowflake would go figure out how to do the distributed compute and create the abstraction for you, such that you could be 2 weeks from school and write the same program and get the result. And so briefly, right, we are building a system called KubeTorch. We gave a talk earlier, which some of you were at, thank you. And so we are designed to make iteration really fast on Kubernetes. This is just my brief hello, like this is also what we do. I think there's a couple takeaways here. There's some APIs, but you can just check us out because I'm running out of time. You can try a few things. I just want to flash to this slide. Run continued pre-training, generate responses, distill the model into a smaller one, which is kind of what NVIDIA also did. Create a high-quality labeled data set of a few hundred examples. Use an LLM and judge to bootstrap the process of getting the data. Use your feedback responses thoughtfully. And like key takeaways, always start with evaluation. If there's no task to optimize, there is no magic. 2, mobilizing data is the magic. 3, you need a platform. And like whether you use KubeTorch or some other platform, you need to figure out a way to do interactive experimentation really quickly in order to get past this prompt engineering wall. And like at the end, like AI ML platform velocity is the same as platform velocity, right? If you're in a DevOps world where you need some guy to help you unblock Jenkins jobs all the time, that's not super good. And so like you kind of want to build the same thing fundamentally across your AI ML applications to do fine tuning. So email me if there's more questions and I'm happy to tell you more about KubeTorch, but thank you.